Hello, my name is Bruce Ableidinger. I work for SiFive. I'm in the architecture group, and I'm responsible for debug, trace, and profile hardware. Oh, here we go. So today I'm going to talk about PathProfiler, what it is, and some features that we've implemented, and some details of the trace format. Cover other ISA implementations, and talk about a little bit about the task group that's been set up for standardizing on this concept. And then I have a conclusion slide. So PathProfiler is a hardware-assisted tool for identifying hot paths in code. So it utilizes a shallow trace buffer to capture uncompressed branch address pairs from and to, or source and destination pairs, and with software does sampling of this trace and captures that and accumulates information about hot paths in your program. I'll talk a little bit more about, we're doing some extensions to add capabilities like measuring IPC and identifying abnormal events like cache misses. So with software, it provides a capability of visualizing the software execution and where the time is being spent. This is an illustration of like an if-then-else-if set of code where it's making a conditional branch based on a test, and then if the branch is taken, then it is captured in the trace, so the red arrows show a path through the code. So these are accumulated with the trace buffer, and then software processes that data. Example would be AutoFDO, which is an automatic feedback-directed optimization program that Google wrote and developed that takes that data and then feeds it back into the compiler to optimize the branches to streamline the program. They've gotten, I think in their paper they wrote, 5 to 10% execution improvement by doing this. So it's a sampling-based branch taken branch trace, and it includes all types of non-sequential execution flows. So conditional branches, jumps, interrupts, and exceptions. And as I mentioned, it's used to optimize program performance. So one of the reasons for doing uncompressed virtual addresses is that it's faster to decode. Traditional trace is a highly compressed trace, like the E-trace or N-trace standards from RISC-V. And they record a synchronization point, and you have to find that synchronization point as an absolute address and then process delta values from there. With this, each record has the source and destination addresses in it. As I mentioned, there's a circular buffer that it's traced into. There's also metadata that can be included, and that's the branch type and number of cycles between the destination, previous destination and the next source, and branch mispredicts. And so this buffer would run continuously, and then it's frozen by either software that's running to sample that, or using a performance counter overflow. For example, it might be counting 10,000 cache misses, and then when that occurs, it'll interrupt and you'll have the 32 branches that led up to that point. Programs like perf, Linux perf, support this kind of capability to sample branches and record those. And there's additional filters. I'll cover that in the next slide here. Our implementation is 32 trace records. We can freeze on the local counter overflow or manually with software writing to a register. Also, a debug breakpoint would freeze the buffer. And we're implementing a programmable timer so that you can do sampling based on the hardware timer, that the lower bits can be randomized to add jitter into the sampling so that it doesn't lock into a particular pattern that might be executing in the application. So the filter types, with the branch information, we can do all branches, all non-sequential executions, or just calls and returns, or exceptions or interrupts. And you can pick and choose which of those you want to include. You can also filter on the privilege level, so that if you're running a Linux application, you use user level filtering. And another is S-context, which is a debug register that was included that when an operating system is instrumented, when it does context switches, it writes to this register and the new process ID, for example, in Linux. And then a debug watch point can be set up to do matching on that value and qualify just on that process. And I mentioned exceptions and interrupts can be filtered in or out. And watch points can also be used to turn trace on and off. So you might have a subset of what you want to measure based on executed addresses. So this is the recording format layout, source virtual address and destination virtual address. And since RISC is a half-word instruction format, the least significant bit is being used for storing valid bit and the branch mispredict. The metadata includes type information and 16-bit cycle count, and also there's some user-definable fields. So what we're doing is extending it to add 16-bit performance counters in those, so instructions retired and load counts, and also 4 additional optional performance counters. Other implementations, Intel has the last branch recorded. It's been around for quite a few years, and it's changed over time, where they first implemented only the from and to addresses, and then they added metadata to that. Now they've recently defined an architectural feature, so all cores will have that with a 32-bit deep buffer and recording the branch types. So the perf, they've extended perf to be able to sample these registers and the buffer, and also set a periodic rate, so it's tied in with perf. The auto FDO and Bolt, which is binary optimization and layout tool that Facebook developed, both use perf to sample the LBR buffers. And in the case of Bolt, that's a linker stage optimization where they put functions, hot functions, if you will, together to lower the miss rate on cache, iCache, and TLB misses. And then ARM has, in the V9 architecture, defined a similar feature. It's quite similar, and they support up to 64 deep buffers. And this is a comparison chart of the three, the PathProfiler, the Intel LBR, and the ARM V9. And I won't go through this. A lot of the similar. One difference, Intel and ARM have transactional memories, and they store status bits for the basic blocks of the transaction. And then I mentioned that we've added additional performance counters into the trace. So recently there was a task group set up to establish the standard for this concept of optimizations through profiling, and it's called the Control Transfer History Task Group. We had our first meeting in November, and we had one last week, so we've had 2 so far. And people are welcome to join this group if they're interested in the features and make sure that this kind of capability is what you want as well. One of the discussions right now is whether this should be an ISA extension and adding new CSRs to support this, or MMIO based, which is more what we've implemented because it's an extension to trace, which is also MMIO access to the control registers and the buffers. So in conclusion, PathProfiler has a number of benefits. The key one is low overhead sampling versus a traditional trace, and like AutoFDO uses this capability in server areas with x86s to optimize branch paths. And I mentioned Bolt, and there's another feature, a Google-based version of Bolt that is also doing this with LLVM, and to couple functions together that are executed often and reduce the cache misses. Also, we've talked with someone at Google who's using it with performance counters, so using it to find abnormal cases and then looking back at what led up to that to provide information on optimizations. I mentioned it's Linux perf supported, and filtering on calls and returns can be quite useful to get a higher level of granularity for doing profiling and performance measurements based on the performance counters that we've included. There's also a mode called call stack where instead of a circular buffer, it records the calls sequences, and when there's a return, it pops that off the stack, so it's just maintaining a call set, and those can be sampled to provide flame graphs, for example. And that can work because it's hardware-based, doesn't require a frame pointer for software to have to walk the stack to determine the calls. And it can be used by debuggers, so it's a 32 deep trace of branches, and you might have a exception occur, and you want to know what led up to that exception, or you might set a breakpoint on a null pointer access and what led up to that. So it can be used as a traditional trace as well. So that's my talk, and if there's any questions. Okay. Thank you.